right, so let's go over some of the commands in Pig. So the first one is load, which is how you get data into the system. And here the data is on HDFS in a Hadoop cluster, and the logical data model, each input data set is assumed to be a bag, which is a sequence of tuples. Okay, so you can specify, you can just say load, but you can also specify the function you're going to use to parse the data with this keyword using. And this seems like sort of just a trivial implementation detail, but it's actually kind of an interesting point and really gets to the heart of one of the problems with mini database products, and one of the advantages of these MapReduce-based systems is that sometimes you're presented with data that's in its raw form, and you need to parse it yourself. Okay, and so the database value proposition is, well, look, design a schema and load all the data into the schema, and after that you'll be able to get all these benefits from querying. Well, look, who's going to do that loading task, right? That's a big parallel job. If I've got 20 terabytes of text files, somehow I've got to manage that computation. And so this is where Hadoop and also therefore Pig and Hive come into play. And so a lot of times what you'll see is that the application for a, say, data science system, data science application will be architected where Hadoop and its extensions are being used to do the initial processing, parsing, and loading, and then the result of that is loaded into a more conventional database for kind of ad hoc querying. And we saw this in the very first segment. We talked about the Obama campaign using this architecture as well. They, at least in an article, you can sort of infer that they had used a similar article. They mentioned Hadoop for the ETL workload, extract, transform, load, another piece of jargon. And then they mentioned this Vertica database for the slicing and dicing. Okay, and you see this. It's almost becoming a standard. I hate to use the word standard, but it's a best practice in designing these kind of data analysis architectures at scale. Okay, so fine. So what's nice about this is that you can specify your own parsing function, so you can work with data in its raw format. All right. And then further, you can specify a schema. If your parsing function is capable of producing lots of different things, you can say, here are the names of the columns that I want to supply. So this is one source of where these column names are going to come from, is you specify them right there in the load command. So this is kind of schema on read, if you will, right? There's no schema associated with the data. It's not self-describing, but you can impose a schema on it as you read it into memory. Okay, fine. And so maybe this is what we get back. We get back a sequence of tuples, and we'll use this as a running example. All right, so the next command is filter, which is pretty simple. You just get rid of some of these tuples, and you can have arbitrary Boolean conditions. You can do kind of regular expressions because everything's very text-based in the Hadoop world, which is in some cases a limitation. And the syntax looks like this. You say filter some big data set by some condition. And so in this case, filter where F1 equals 8. And remember that F1 was the name we gave it in the load command, the name we gave to the very first column. And so this finds all the tuples where the first position is equal to 8. Fine. So another command is group, which is bringing data together. Okay, and so there's a couple different forms of this. But we're going to focus on, so this, just right now we're just talking about group. Okay. There's a co-group command that I'm going to talk about in a moment. All right, so group says, group this large data set by some sequence of columns. Okay. So this looks a lot like the SQL clause that's the same, it got the same sort of flavor. But it does something pretty different. Okay. So if this is A and we group by F1, well, what we get out is tuples, but now the first column is the same because we grouped by F1, but the second column, the second field, I should say, is now a bag, a little group representation of all the tuples that were associated with this particular key. And so if you look over here, there's only one tuple with 1, and that tuple appears in the group. There's 2 tuples with F1 equal to 4, and so this bag has 2 tuples in it, and so on. Okay, so this is how you can start off with something that's kind of a flat structure, and you can build up a nested structure for various reasons, and we'll see why. Now, the other thing to keep in mind, and this is another thing I don't really love about Pig, because they're doing things sort of implicitly rather than explicitly, is that the name of this field, every field ends up having to have a name, and so the name of this field is defaulted to the name group. Yeah, sorry, I just lied. The first field is defaulted to the name group, and the second field is defaulted to the name of the original data set. And so I find this a little confusing when you're writing pig yourself, but you can sort of see why they did it. The reason is that just these bags all together actually have the same information as the original data set, just nested in a certain way. And so calling it A sort of makes sense. It's got all the same information. So for example, notice that the value 1 is now repeated twice, once in the group and it's still in the tuple. Okay, so fine. So there's also a command distinct that does just what you might imagine. It gets rid of all duplicates. And just for a simple example here, if you've got two different elements in the bag that have the same value, your output will be this. Okay. I might make a claim that distinct A is equal to grouping of A by all three columns at once. So first of all, why am I making that claim? Well, remember that the group operator puts out a single tuple for every unique value of the grouping columns. So that sounds about right. And you can also maybe think from if you know SQL, that this is sort of true there, right? You can use this distinct keyword in SQL, and you can also group by all the columns, and you'll end up getting the same result. So are these two expressions the same? Do they produce the same output? Well, not quite, because the grouping structure, the group command produces a group field, which is now the whole tuple, excuse me, and the A field, which is a bag with a single tuple in it. So you get this sort of repetition of information, so distinct is much more concise. So you need to be careful and sort of make sure you understand what these things are going to produce. So how does group work? Well, we already saw, going back to our MapReduce schematic or our parallel processing schematic, we break the data into pieces. We apply a map function that assigns each tuple to its key and groups the tuple to in the value as well. And so here, if we group by F1, then F1 becomes the key, and the value is all three of the elements in the tuple. And those are shuffled across the network to the reduced side, and the reduced side will construct this bag type out of the set of tuples. Okay, so this is a single MapReduce job. All right. So the for each command is almost certainly the most complex one. So here you're basically going to manipulate each tuple in a bag. So you write it like this. You'll say for each A, generate something. And here we're generating a tuple with two fields. One is F0 and one is the sum of F1 and F2. And here you can call user-defined functions, or you can write other kinds of arithmetic expressions. You can sort of do lots of things. Okay. Fine. So another example is first we group A by F1, just like we did in the previous slide. Excuse me. This should be Y. And then for each Y, generate group. So what's group? Well, remember that's the magic name assigned given to the group field. And then Y, which is the magic name given to the bag field, dot a list of projection columns. And so this is the second element and the third element from each of those tuples. Okay, so what does this look like? Well, X, which is this first element here, well, we get the first field from A, which is this column here, and then we get the sum of the second two. So 2 plus 3 is equal to 5, 2 plus 1 is equal to 3, 3 plus 4 is equal to 7, and so on. Okay. Then down here for Z, remember that Y looks just like it did in the previous slide. Here. Oh, well, no, sorry, I didn't actually do the complete example of Y. So Y is all of A grouped by the first field. But then we're going to generate the grouping field, which is the same. and we're going to project out the second two columns. We're going to ignore the first column in each one of the bags. Okay. And so the point here being that you can manipulate these nested objects by writing these kinds of expressions. But I think the other sort of lurking point here is that it's a little bit complicated to think about what's going on because of this extra flexibility you get with the nested data model. Okay. So you'll get a chance, in the assignment, you'll get a chance to try some of these out and make sure you understand what they're doing. Okay, so then there's this keyword flatten, and it's not really its own operator. You use it in the context of for each. And so here, you know, because of the complexity here, what you might really want is, look, I just wanted to get rid of the, if you want to recover the flat version of the nested structures created and stored in the variable z, well, you can do so like this. For each x, generate group and then the flatten of x. And the result you'll get out here is, but regardless, what it does is sort of peel out this bag and produce an extra tuple for each. And I don't really like this because it sort of changes, just using the keyword flatten changes the semantics of the for each and generate. And I think it's a very, very confusing way of doing it. So the idea, it's hard to explain the principle going on here. Just sort of memorize what it does. Practice with it and memorize what it does. All right.